So part A, if you take the derivative of the right, that's what they want you to do there. For part A, to verify, basically you just have to differentiate the right-hand side and get x cosine x, right? If you do that, what do you get? Negative sine x plus sine x plus x cosine x. So these two cancel, so done. Right? Oh. So yeah. Do you need help with part B? Yes? Did you say yes, part B? Okay. 56 from 7-2. This one? Oh, that looks interesting. What does that mean, couched? So identify the integral that represents the volume of the solid obtained by rotating the area between... Oh, so you just have to pick one. So is it A or B? B. So it's the difference of two volumes, not the difference in the areas. So B. That's it. Oh, so far so good. Any other homework questions I can knock out this fast? So don't ask me like, those fun ones at the end, because that'll take us a while. Like, that's what I was referring to. Yeah, probably not. I'm not going to do 73 now. We can talk about it after class if you want. You have to realize when this is the thing you're trying to find the volume of, right? So each cross section is a square, right? That's the nice part. So it will allow us just to add up all the little rectangular tiny boxes along the y-axis. So you're going to have a delta y times the area of the square. Now the area of the square, you have to define it in terms of the points where the cylinders intersect, right? So we have to get a little bit creative on that one. So we can talk about it during office hour or whatever. It'll take us a little bit. Same thing with like 79. So where are we? Okay, so I want to revisit some of the results we got. So yeah, so here the answer is just B, just based on what we're talking about. So I want to revisit some of the results we accomplished on Monday. So we were talking about the arc length, and then we kind of went through that painful derivation of the surface area. But I want to talk about this idea, and your book doesn't stress it at all, but it will come back in Calc 3 to you. Because in Calc 3, you're still going to be talking about the arc length, only now instead of having a two-dimensional curves, you can have a three-dimensional curve. So you'll be parameterizing those, and it's going to have a lot of fun with that. But what will come in useful in Calc 3 is this notion of an arc length parameter. So I'm going to do a lot of writing because it's not really in your book. So from Monday's class, we talked about the scenario where you have a nice differentiable function, and we can literally find the length of the path of that portion of the graph. Now, it's really irrelevant where this graph is, above the x-axis, below the x-axis. None of that will matter, because if you recall, when we derived the formula, so your book uses the little s for the arc length. The formula um, from Monday's class was just the square root of 1 plus the derivative of x. I mean, derivative of f of x squared dx. And so just the way the formula is written, it doesn't matter whether f is positive, negative, it's going to come out. What was that? It's going to come out positive regardless of the, yes, from A to B. Regardless of the orientation of this graph, the answer will come out positive. Well, now, what I want to play with, instead of computing, so I'm going to write it down, this big paragraph. Instead of computing the total length of the curve from x equals A to x equals B, so instead of computing the length, we're actually going to stop at some point, well, let's call it t. So we're going to compute the arc length, the length of this curve from initial point A all the way to some point t. So this point right here is t, f of t. And this point right there is a, f of a. So we are computing the length of only a portion of the curve from x equals a to x equals t.
Yeah, you have to adjust the integral.
What?
You not just replace t.
Well, that's what's going to happen. I mean, b becomes t. I mean, right? It's still you're looking at this little chunk, so I can actually look at s as the integral from a to t, the square root of 1 plus the derivative of f squared dx. But now this is a function. I mean, s is a function of t now. It's whatever the t is, right? S varies with respect to t. So s is your dependent variable. S varies as t varies. While t is your independent variable. So there's nothing really special about this definition in comparison to what we had so far. Just again, to make sure we understand what it does. I mean, if I ask you what is S of A is, what do you think that would be? 0, right? The answer is 0 because you're just looking at the integral from A to A of, 1 plus f prime squared dx. That's clearly 0. And if I ask you what S of B is, well, that's just going to be the length of the entire line segment, right? If t equals b, so you get the length of the segment. Well, but you see this notation now, this is S of t. So S of A means A goes where the T is. So you end up in it from A to A, right? So I'm basically putting T where the A is. So then there is nothing there. There's just a point. Well, yeah, you kind of did that in Calc 1. You defined functions in terms of integration. And so you had the area that varies depending on where you put your variable in. Here you have the length that depends on where you put the variable in. But if I differentiate that, if I actually compute so this function S is called the arc length parameter function. And if I compute ds dt, what does that equal to? If I take the derivative of this function with respect to t, what do we get? Yes, right. That's your FTC. That's the fundamental theorem of calculus part, well, according to your book 2, according to the rest of the books 1. But it's the one that you don't see very often, okay? So let's just call it fundamental theorem of calculus. You just get the integrand, the square root of 1 plus f prime of t squared. That's the fundamental theorem of calculus. And also the differential of s is the square root of 1 plus f prime of t squared dt. So this is ds right here. And you saw at the end of Monday's class where we were doing the surface area of revolution, I mean, we had that this chunk, I mean, only dx's. That's irrelevant. So we just call that a ds. So we can actually set up those integrals with respect to the arc length. And we'll be doing a lot of that in Calc 3. They'll show up, those little ds's. This? No, that's enough. So that means t equals b. So t equals b. So you get the whole curve, right? You just get that. So it's, right? But anything in between, I mean, if I give you a value, you can compute that. Well, let me give you an example. We're just going to take a function, and we'll compute the arc length parameter. And it's going to be a fun little function. So given the curve y equals x squared minus 1/8 ln of x, find the arc length parameter starting at the point 1, 1. So, I mean, we don't really need to know the graph, what it looks like for these types of problems. But, I mean, it won't hurt. I mean, if you think about this, can you picture that graph? So x squared is a parabola, right? Now, natural log limits the domain somewhat, right? So what is the domain of this? Right, so from 0 to infinity. Now, the natural logs, so think about this. The domain of this function is from 0 to infinity, right? So there's nothing to the left of the y-axis. So if I just think about the parabola, here's the parabola. Now, what does the natural log does? So at 1, the natural log is 0, so this thing will be the same, right? The point of the function will be on this parabola. But for the values that are greater than 1, natural log is positive, right? So you're going to be subtracting a positive number from your parabola, and that positive number gets bigger and bigger and bigger and bigger, but kind of slowly, right? So you're basically going to have kind of a slower growing parabola, right? But on this end, the natural log is negative, right? So you're subtracting a negative number, so you're actually adding something to a parabola. So you should get points. So you're going to get something like something like this, okay? So anyways, that's almost irrelevant. But it was a fun exercise in thinking out loud and whatever.
Like the point, right?
Uh, well, it won't, because as you get closer to 0, natural log gets infinite, right?
Yeah.
So as you're getting closer to 0, you start adding larger numbers. So I mean, you still have the asymptote here, and it'll shoot to infinity. I mean, let's just grab this thing. What are we doing? But do you see what I'm saying?
Yeah, but it gets really close. I don't know.
Yeah, I mean, it'll have this asymptotic "I'm about to touch you" thing, but it won't, right? Um, where's our full plot? So what is x squared minus 1/8 times natural log of x? So you see, it does do that. I mean, see, it gets very close, but it keeps playing the asymptotic game, doesn't it? Or does it? No, it doesn't hit it, right? Yeah, I don't know where I'm at right now. You won't touch it. It's not supposed to. 0 is not a part of that thing. Um, but anyways, so let's compute this thing. So we just want to compute the s of, s of t. So that would be an integral. Well, I don't know. That's the thing. I'm just doing the parameter thing. So I'm going to go from 1 to t, right? So here's that initial point. So that part doesn't even matter. I'm going from 1, 1 on to whatever the t is. So now the rest is just like what we did on Monday, computing the arc length. So we have to be taking the derivative so derivative of that squared. You know what I'm writing in there. It's hard to see. But so for Monday, we want to take the derivative, square that, mess with it till we get the perfect square, right? Because then the square root helps. So first, let's just take the derivative of x squared minus 1/8 ln of x. So what is that? That's simple, right? So it's 2x minus 1 over 8x. Is that okay if I write it like that? That's just the derivative. Then I want to do 1 plus that derivative squared. Now again, remember from what we discussed on Monday, I want to mess with it. I want to make it a perfect square. And we saw a little thing on Monday that it's that might almost work. Let's see. So 1 plus 4x squared. Now 2 times 2 times 1/8, x's cancel. So it's negative 1/2 plus 1 over 64x squared. Is that okay? If you square that thing, the middle term is negative 1/2. So 1 minus 1/2 is positive 1/2. So we are, you saw that it's a very similar example on Monday, where you see that the only thing that changed basically the sign of 1/2. So that means this can be factored back into 2x plus 1/8 x squared. Is that okay? Well, uh, I mean, I know that this came from that. Well, so the only thing changes the sign in the middle, so I'm just going to change that sign. So good, perfect square, so that means I can take a square root of that. So my function is the integral from 1 to t, the square root of 2x plus 1/8 x squared dx. So the square root and the square go away. X stays positive. From 1 to t, 2x plus 1/8x dx. Is that right? What was that? Well, but I know I still have the square, so the square root will get rid of the power, yeah. So yeah, these problems are very carefully, designed so it works out that nicely. So anyways, that's easy to integrate, so that becomes x squared plus 1/8 ln of x, evaluated from 1 to t. You plug in t, you get t squared plus 1/8 ln of t, but then minus what? Just 1, right? You plug in 1 squared is 1, ln of 1 is 0, so minus 1. So this is the function. This is your arc length parameter. So now given the t, it will spit out the value of the arc length from 1 to whatever the point you have in mind. But of course, ds here would be 2t plus 1/8t dt. Right? Just like, the fundamental theorem of calculus suggested prior.
Like in every problem we've gotten so far, the only thing that changes after you take the integral is like the plus.
Well, yeah, that because this is so the factoring works out. I mean,
You're pretty much taking this, like your function, taking the derivative, and then swapping the plus and minus around and taking the integral.
that's what happened so far. I mean, you'll end up with different functions under that square root, but you want to have that perfect square. I mean, if you don't have a perfect square, you're going to have to get very creative. And after we get through chapter 8, I mean, as we're going to be studying the new and newer techniques of integration, this thing will come back. It's like, hey, how about this arc length? Because now, doesn't come out as a perfect square, but you can still integrate with those newly developed integration techniques. Well, because I mean, that's how we define that thing, right? I mean, this is the definition, basically. So, I mean, one benefit for now, it's very little benefit, is that now given the t, it'll basically a function of arc length. But this ds thing will be very useful in Calc 3. It will come up. And I'll show you this in a second when we're actually going to be doing because we haven't done any examples with the surface area of revolution. Because if you remember from Monday, you had kind of that thing at the end of the formula. And the formula for the arc length, you kind of need to know. I mean, this is the formula that you need to know, basically. But the formula for the surface area of revolution, you can kind of come up with that formula, not going through the hell of whatever we did on Monday. But remember what the whole message on the Monday's class was. After we went through doing what were we doing? We were doing the cones and we're counting them and we were averaging the heights. But then we realized that, when I do this rotation and I want to find the surface area, again, I'm taking those little strips, right? And I'm finding the area of each strip, and then basically it came down to whatever the arc length is, so S, times the height. All right, the circumference is 2 pi r, and the r is the height. So the formula that came out was what? So I think your book uses the big S for the surface area. So it was 2 pi, what? I know we were using A last time, but the formula came out to be 2 pi. So the height, I mean the radius is f of x, or the y, whatever you want to call it, f of x, and then the arc length. That's how you remember that formula. Okay, it's 2 pi r times this little thing. But again, this right here is ds. So I can think of the same formula as 2 pi from a to b. F of x, that's my y, and ds. This is kind of a weird way of looking at that formula. It's still set up as a dx integral, but the arc length is irrelevant of how we compute it. I mean, if I flip my formulas, if I try to compute the arc length and I solve for x in terms of y and I do it as a dy integral, I'll still get the same length, right? So you'll see examples where it's actually, you can just flip from dx to dy with relative ease. I mean, I'll do something painful, but then we'll see that you can just remember the Alex's pain and we can just do it. We just flip from one to the other without going through the motions. But, and this part is going to be a little bit confusing for now, but yeah, this would be the surface area of rotating around the x-axis. But again, ds, you can do the ds as 1 plus, dy dx squared dx, or you can do that one as 1 plus dx dy squared dy. Of course, your a and b would have to change. I mean, you have different limits, okay? So you're probably going to be from c to d if you flip your variable of integration. And if you rotate around the y-axis, you're going to get a different surface area, but the arc length portion will basically stay the same, because now you're looking at an integral from c to d. You have some, not f of x as the originally, have some function of y now, some g of y, and then 1 plus that function. But again, this is some x. You can always think of this, and this is ds. So you can think of this in those terms as well. So let me do a few examples. Some of them going to be silly, where we don't use any of that ds, dy, dx flippage. We're just going to do them straightforward. And then I'm going to do a few examples, maybe just one example, where I just do both ways. And one of them, I mean, both of them work. They both give you the same answer. One of them is going to be less painful than the other, and then I'm going to do something really painful. But through that painful birthing process, something will come good, maybe, hopefully. Okay. All right, so let's do some. Basically, we're just going to start with doing the surface area of shapes that we know the surface area of, just kind of to check our formula. So let's do a surface area of a cylinder. So one way to think about this we can generate a cylinder by rotating a horizontal line around the x-axis. You'll get a cylinder, right? So let's say this is A, this is B, and let's say, this is the R. Now again, bottomless and topless cylinder, of course. We're not doing the areas of the bases and the tops, just the walls, right? Without doing any calculus, can we figure out the surface area of, of that thing? It shouldn't be hard, right? Yeah, so because when you cut it, you get a rectangle. This is the circumference, which is 2 pi r, right? And the height, what would be the height? It's whatever this length is, right? So it's 2 pi r times the height. And in this case, the height would be b minus a, right? It would be the height of that cylinder. But if I follow the formula, we can just set it up as a dx integral. The formula tells me that it's going to be 2 pi, an integral from a to b. Well, what is my function here? Y equals r, right? This is the function, y equals r. So this is r times the square root of 1 plus the derivative of r squared dx. Right? So what's the derivative of r? 0. R is a constant with respect to x. So I can actually pull r outside the integral. The derivative of r equals 0. So all we have is ab dx. The integral from a to b dx. So what's the integral? Just x, right? The antiderivative of 1 dx is x, so we get 2 pi r, x evaluated from a to b. What? Yeah, b minus 8. Okay, so good. Makes us partially happy. Questions how we got that? That's straightforward, right? Let's do the surface area of a cone. So we use that formula. We derived that formula using just basic geometry, and that formula came out to be that the surface area is pi r L. Now, to set it up kind of using calculus-y techniques, so it is 2 pi, but before I go 2 pi and all that, let's just think about how to generate a cone. So we can generate a cone by just rotating a straight line that goes through the origin, right? So, so this point right here would have to be, this is H, and this is R, so it's HR, right? So it's generating, rotating a line that goes through the origin and point HR, so that produces a cone, right? So what is the function? What are we going to rotate? Can we come up with that function? Well, but just y equals mx plus b thing, right? That's the line. So the slope is changing y over change in x, right? So y equals, that way equals what? R over h, x. The y-intercept is 0, so that's it. That's the function. Is that okay? That's what we're going to rotate. So then it's the integral from 0 to h, the function r over hx times the arc length, which is 1 plus the derivative of that squared dx. Yep. So what is the derivative? Oh yeah, I'm going to pull out a whole bunch of stuff out of there. But yes, I can pull out RH. But what is the derivative of RHX? RH, right? So after you take the derivative, you're going to end up with R over HX, the square root of 1 plus R over H squared dx. Right? That x went away after you took a derivative. So actually this entire square root is also a constant. So I can remove it. Do you agree with that? So if I pull all those constants out, we get 2 pi r over h times the square root of 1 plus r squared over h squared, and then the integral from 0 to h, just x dx. Is that all right? Yeah, I mean, after I take the integral, because I'll get x squared over 2, so plug in h, I'll get h squared over 2. So many things will cancel. We're going to make it pretty. It's not pretty yet. And then it's x squared over 2 evaluated from 0 to 2. Not from 0 to 2, from 0 to h. So you get this. 2 pi r over h, the square root of 1 plus r squared over h squared times h squared over 2.
So then, the square root is...
Well, eventually, yes. Yeah, after you manipulate a little bit, you're going to get your L out of that. But you're right. So, because look, I can cancel the 2's. I can cancel one of the h's. So I have this. I have pi. I have r. But then I have this lonely h over here, right? If I push this h under the square root, what will happen with that h if you push it inside the square root? becomes h squared, right? So that becomes h squared times 1 plus r squared over h squared. It gets multiplied by the radicand. So then you distribute it, you end up with pi r, the square root of r squared plus h squared. And that's L. Well, just like you can take something from the square root by taking the square root of it, you can put something into the square root by squaring it, right? 2 square roots of 2 is the same as square root of 8, because, hey, if I put 2 back on the inside, it becomes 4 times 2, and then it goes there. So you can do it both ways, right? But r squared plus h squared, r squared plus h squared is L, square root of that. So we're good. No, it's still complex. It's one of those overkill problems. We can do these formulas a little easier, but the surface area of a sphere, will benefit from this technique. So let's do that. Yeah, we did that one in class, right? So it's basically the same problem, but it's just too good of a problem to just leave it as a homework and I don't get to talk about it because I like to talk about it. But let's try the volume, the surface area of a sphere. So, we know that the surface area of a sphere is 4 pi r squared. But now we can derive it, and we can derive it in the following way. Again, we're going to take a circle centered at the origin of radius r, and then we can take the top semicircle from negative r to r and rotate it around the x-axis. We'll generate a sphere, and then we can just talk about the surface area of that. So the function here would be y equals plus or minus the square root of r squared minus x squared. And since we agreed on the top semicircle, we're just going to take a plus. So what? Length of... No, the length from negative r to r is just, the arc length, yes. It will be part of the formula. But yeah. So the surface area, if we do that, so it's 2 pi, the interval from negative r to r, the function times the arc length, which would be 1 plus the derivative. Okay, there's no way I can squeeze it into something that small. So it's 1 plus the derivative of this square root squared still under the square root dx. All that's in the integral from negative r to r. Now, of course, we can go from 0 to r and double that whole thing, right? It's symmetric, so we're just probably going to end up doing that. Go from 0 to r. Okay. So probably have to do, this is 1 plus all that. So let's do some of these things on the side. Let's just compute the derivative of the square root. So what would that be? Right, so it's 1/2 that to the negative 1/2 times the derivative of the inside, which is negative 2x. Right? 2's cancel, so I can actually write it as negative x over the square root of r squared minus x squared. Right? Well, I mean, it gets squared, right? So when I actually compute, when I compute 1 plus the derivative squared, this is going to be 1 plus square that, so that's x squared, and the square root goes away, and the negative goes away. Is that right? I mean, it's still under the big square root, but hey, I'm just doing it by, step by step. Is that okay? So now, I mean, if I do the common denominator here, if I actually add 1 to it, so the denominator is r squared minus x squared, so you'll get r squared minus x squared plus x squared. So x squared cancels, so you end up with r squared over all that. Is that right? It's just this part right here. That's what we got so far. I can actually go ahead and start putting it all into one integral. The rest is actually going to be, it's not that bad, actually. It's not that complex. So let's put it all together. So instead of going from negative r to r, let's go from 0 to r and double everything, so that becomes 4 pi. Is that okay? And then, yeah. And then you have the square root of r squared over r squared minus x squared dx. So you see what's going to happen with that big expression? I mean, all the square roots go away, right? I mean, if you write it out, this is 4 pi, an integral from 0 to r, the square root of r squared minus x squared times the square root of r squared is r is positive by definition, over square root of r squared minus x squared dx. So the radicals just go away. R is a constant. I can pull that one out. So it is 4 pi r, and then integral from 0 to r dx. And then, well, that integral is just x evaluated from 0 to r, which gives you that extra r. So 4 pi r times r, 4 pi r squared. Isn't that nice? What? Well, I'm glad you mentioned that because I'm about to do this problem. Where it's, well, this is, I'm going to jump this question. I'm going to go, say I even have a crying sad face here. It's part of my notes right there. I was very sad. Um, but anyways, hey, we just got the surface area of a sphere. That's a big moment in our development. So I want to do the surface area. I'm going to rotate this function. Again, I'm going to do one of those squares minus ln functions, because as you notice, they work out nicely with the square roots. But I want to rotate around the y-axis. Right, surface area, finding the surface area. So again, the graph of that thing is kind of a parabola. When you start from 1, natural log stays positive. You just subtract things from parabola, so you get something like that. So you rotate it around the y-axis. You know, you get this thing. Okay? Yeah, there's a hole in the center. But it doesn't matter. We're not doing the volume, we're just doing the area, right? So I'm not, you know, yeah, okay. Yeah, just the really thin. You're just finding just the area. You're not rotating, you know, the region bounded by the thing, which should produce the same surface area. Just, you know, you don't need the substance on the inside. But again, it will just not going to give you anything. You just get a volume. So what? Do you have a... No. Well, ideally, yes. The volume of, you know, a piece of paper should be very small, right? I mean, here's a true embarrassing story. I shouldn't be recording that, but so I was painting the walls in my, you know, whatever living room, and here's a very common mistake. I was trying to figure out, you know, the surface area of the walls, which is a very simple problem. But for some reason, I ended up computing the volume of the living room. And I was like, whoa, that's a lot of paint that I need to buy. And I was just looking at this can't be right. So I was actually going to the store buying enough paint to fill my living room entirely. So these are the two different concepts. So now we're talking about surface area. You're just painting the walls. No, I looked at it, I was like, no, that can't be right. It just, yeah. So, which is a very convenient way to paint the walls. I mean, you will still get painted, but yeah. Well, then you just kind of siphon the paint out, the walls still get covered. Sure. But anywho, so this is what I'm talking about. Let's not remember the formula for the surface area. This is the formula you kind of want to almost forget, but know how we came up with that formula. Because if you think about this, again, we're doing those kind of strips, right? We're just going to slice it, those little strips. And we agreed that the area of that strip is the circumference times the length of that side, right? So the circumference is 2 pi r. Now, if I think about the radius, well, the radius is whatever the x value is, right? Whatever the x is, that's the radius of which one of those strips. So if I set this up, I'm going to get 2 pi times the radius, which is x, right? I mean, x is probably some kind of a function of y. We'll talk about it later. And then times the arc length. So I'm just going to toss that ds guy. I mean, not dx, ds. ds guy in there. But where are my notes? Here we go. From evaluated from whatever this point is to whatever that point is, from C to D. Now we're going to put some numbers to it, and we're going to see the pain that we might end up in. So here's the pain. Well, first of all, in order to compute ds, and I'm rotating around the y-axis, ideally, I do want to do the dy integral. And if I set this up using the dy integral, I'll get 1 plus, then I need derivative of x with respect to y. So this is dx dy squared dy, right? I need, that's the thing, right? Can we do that? I mean, that's what I'm going to start playing with. But yes, you're exactly right. I'm going to start messing with taking the derivative of the inverse, and basically I'll convert it into dx integral. And this is going back to I was saying earlier that when I was talking about this part, that really when you look at this portion, you can either treat it as a dx or a dy integral. But now this is going to be that slightly painful process of manipulating that into a dx integral. Because look, well, first of all, my limits of integration would be, yeah, so it's from x goes from 1 to 2, so y goes, when you plug in 1, you get just a quarter, right? This is y of 1. This is y of 2, right? If you're looking at the dy integral. So this whole thing becomes 2 pi, and then the integral from 1/4.
Wait. So the question, did you know, like the x integrals have the limits there, and then you know the radius is x, you could solve for y in terms of x,
But it's already,
or solve for x in terms of y.
I want to avoid doing that really hard.
But why? Because, I mean,
Well, I mean, can you solve for x in terms of y?
well, I'm just saying you can find the radius in terms of y.
Well, I mean, you can,
So you have your 2 points, and then, like, so it's like you have your 2 points, you find that, like, relationship.
right, but the relationship happened to be messy.
All right.
I mean, we know the relationship. But anyway, so for now, this is 1/4, and when you plug in 2, what do you get? 1 minus ln of 2 over 2 as your limits of integration. And then this is x. And again, that stays the same. So yeah, this is where I drew my very sad face. This is the part with the sad face. And it's crying. Because didn't understand why it's sad. I mean, but Dalton is exactly right. We can do some manipulations here. We can use the idea of taking the derivative of the inverse, because we, in order to solve for x in terms of y, we're really looking for the inverse function. But just playing with this, let me go back. Do you remember from Calc 1 the derivative of the inverse function? How do you find the derivative of the inverse? But there's a quicker way. Well, you proposed that. No, I remember. I'm just trying to see whether I'm remembering correctly. I mean, we can think about it this way. I mean, we can just think about this algebraically, that dx dy squared is the same as 1 over dy dx squared. Can we think about it that way? Yeah. So this is. So then you were talking about reciprocal. Oh, okay. Well, this is why we went into inverse function. But anyway, but yes, so we can flip this around. 1/4, 1 minus ln of 2 over 2 x. Then here I'm going to write 1 plus 1 over dy dx squared. And here, instead of writing dy, I'll write dy over dx times dx. It's the same as the previous problem. The only thing is I should probably fix those back to x. Because I'm ending up with the dx integral now. What? Well, I just, instead of writing dy, I wrote dy over dx times dx. Same as dy, right? But what will that give me? I have a dx there in the end, and x ranges from 1 to 2. So this is 2 pi, the integral from 1 to 2, x dx over here. But now, as we discussed earlier, if I push dy dx inside the square root, it gets squared. So this gives me dy dx squared times 1 plus 1 over dy dx squared. Right? So you distribute that, dy dx cancel, and you end up with 2 pi, the integral from 1 to 2 x times dy dx squared plus 1 dx. That's exactly the same as just integrating with respect to y. So this is what I was saying. This was the arc length computing with respect to y as a dy integral. Now, after this painful process, you get the same exact thing, only it's still your ds, it's still the arc length, only computed with respect to x. So this is, why that's kind of allowed. If you just think of this with respect to the arc, length, then you can compute arc length in a multitude of ways, and then you just choose the one that's more convenient. Well, that was the original proposition for the x. So x ranges from 1 to 2. Y ranged from this ugly thing, but doing the dx integral makes it all. Because now we can take the derivative, because now it's dy dx, I can compute the derivative. I can square it. I'll probably end up with a perfect square because we've done that, right? And all it just has an extra x on the outside. Oh well. I don't know if I want to go on with this problem because we got it to the point of it's no longer a set phase. Yeah, we'll probably have enough time to finish this. I mean, if we finish this, so the function, so first we need the derivative. So the derivative, it was, what's the function? 1/4 x squared. So the derivative is 1/2 x minus 1/2x. Right? Is that right? It looks, you have to be very careful when you write this thing down. It's very easy to really easy to mess it up. So 1 plus this thing squared gives you it's not going to work out as nice. Maybe I shouldn't have. What's the middle term? Oh, so it does work out. So it's 1/2. So we'll want to have that 1/2 in there, plus 1/4x squared. So when you combine like terms, it's 1/4 x squared plus 1/2 plus 1/4x squared. So that's a perfect square. Is that okay? So then it's just 1/2x plus 1/2x, quantity squared. So now it's under the square root. Yeah, this is just, you have to be very careful when you write this thing down. So it's 2 pi, the integral from 1 to 2 x times the square root of all that. So the rest should be okay. For 1 to 2, x times 1/2 x plus 1/2x. Distribute the x. We can pull 1/2 out, so that just makes it pi, right? From 1 to 2, x squared plus 1. Is that okay? So then integrate, that's the easy part. X cubed over 3 plus x from 1 to 2. So what do we end up with? Pi times 8/3 plus 2 minus 1/3 minus 1. Yeah, so it's 7/3 plus 1, so it's 10 pi over 3. Something squared. Greg? Is that okay? But again, the whole thing here, this part, like this whole part from the set phase and the Up to here, you don't need that. You just remember you can manipulate these types of integrals in that fashion. You can very easily go from the y integral to the x integral without really changing your radius function. Okay, so I want to do this problem. So rotate y equals x squared, where x is again from 1 to 2 around the y-axis. So this is just a parabola, nothing fancy. So the points are 1, 1, 2, 4. So it doesn't have that natural log there. So we just want to do the surface area of that thing. So around the y. And I'm going to do this both. This problem can be done both ways, because again, it's, if you need to get x in terms of y, that's easy to do, right? So I'll do it the easy way first. I'll do it the easy way, and then I'll do it a little, it's a little messier. Get the same answers from both. So rotating that way. So again, don't need to memorize the formula, just to understand the logic behind that formula, that it's the circumference of that thing times the little arc length. Okay? So again, if I think about that way, the radius, I can just think of the radius in terms of x. Right? So then the surface area is 2 pi x ds. Now, if I do this dx style, because again, when I see x here, so it feels like, dx integral is very friendly. So if I do the dx integral, so x ranges from 1 to 2, right? And then I need to do the ds in terms of x. Okay? So that means the whole thing is 2 pi, the integral from 1 to 2 x times the square root of 1 plus the derivative of y, right, dy dx squared dx. Is that okay? So this is just doing it a dx style. So if we continue with this, now from here on, that's a Calc 1 problem. That's a straight up integral, x, the square root, the derivative is 2x, you square that, it's 4x squared, so 1 plus 4x squared dx. Right? So this is now we actually like that we have that x on the outside. If this was just the arc length problem, it will be very hard to do, but that x makes it easy to do, right? Yeah, you just let that be u, so the du is linear, so it'll work out. So we're going to run the u sub through this. Let u equals 1 plus 4x squared, so then du is 8x dx, right? So therefore dx is what? Du over 8x. So then this becomes 2 pi, and integral, let's just put it all in terms of u. So this is u of 1, and this is u of 2, x square root of u du over 8x. So x is canceled. 1/8 comes out. So 1/8 comes out, makes it 1/4 pi. Now u of 1 is what? 5. And u of 2, 17. 17, is that right? Yeah. 17, and this is just, u to the 1/2 du. Is that okay? So then just integrate that. So 1/4 pi. So what does that give me? 2/3 u to the 3/2 from 5 to 17. Yeah, there. But so 2/3 gives me pi over 6. And then you have 17 to the 3/2 minus 5 to the 3/2. Or it's 17 square root of 17 minus 5 square root of 5. Whatever that is. That's an answer. Is that okay? Okay. Questions on how we did this one?
You know how system teaches you what's the call? You just have to like replace a certain bolt. You don't know why. You just Rx down and just replace that bolt. I feel like this is what I'm doing the problem. I like see what makes sense how it correlates.
What do you mean? I mean, like, I'm not sure I understood. I was with you.
Like I can
I was with
understand.
you with the bolt in the car, and
I mean, I can understand like you have your surface area, and you give us like a support some sort of. I mean, I get that it's like with circumference. I don't know. There's like not
yeah, but
circumference
that,
changes.
but those were those birthing things that we did. That's what, the one that we did, the really painful one from Monday. That's the, it's really hard. It's I thought you were gonna go with the, one of them. Where am I gonna use this thing? That's what I thought you were going for, which I don't have the answer for. But. Well, it just turned into u, right? And then I changed the limits of integration in terms of u, so I don't have to substitute back. Because remember, when you do the definite integrals with u sub, you just want to change all the limits. So yeah, I mean, I did show you why that's the thing and why is that the arc length and all that. I'm gonna clear on that one. Now, where are you gonna apply that besides painting your living room? That's a different story. Well, let me do this dy way. Let me do this dy way. This is gonna be a little messier.
Like, how would you make a resolve that ends up being like cute?
Well, you don't. That's a different thing. But I mean, the cube again. You could take the same concept. You slice a cube into many little things, and you find the surface area of which one of those things, and then you just add them up by whatever axis, so you don't get the 2 pi part. Well, this is kind of the way we did, the Froströms and those guys. When you have consistent cross-section. I mean, you can do it the same way, which is, of course, an overkill for a cube, right? But I mean, the question is, if you take a cube and, and you twist it, you keep it the same height, I mean, is it going to maintain the same surface area? Because is it going to maintain the same volume? If you take a cube and you kind of twist it, but it still has the edges, so the cross sections are all. Yeah, it will. I mean, you proved it on the homework. And, your Rubik's Cube, you twist it, it's it's the same volume. You don't do anything to it. But is it going to be the same thing with the surface area? That's a different question.
Because then you have like, I'm just certain that if you're actually talking about a Rubik's Cube, if you twist it, you have one edge of the counting.
Well, but this is what, I mean, the Rubik's Cube example is probably, this is how we approximate this, by literally looking at those blocks that are kind of discrete. But if you make that nice, pretty, continuous twist, that's what we're kind of trying to. Anyways, can I do this dy thing? I mean, we can discuss those concepts a little later. I mean, this is what we did the math club for, to talk about stuff like that. So again, I want to do the same thing, only I want to do it dy way. So if I set it up as a dy integral, so then it will be 2 pi. Well, y ranges from 1 to 4, right? If you look at the y-axis. From 1 to 4. Now the function was y equals x squared, so now you have to actually solve for x in terms of y. So that's that. So x becomes square root of y, and then the arc length is 1 plus the derivative of the square root of y squared dy. Only we're going to do the derivative with respect to y here. It's a dx dy thing. Okay? So from 1 to 4, square root of y, and then this is 1 plus, the derivative of the square root is 1 over 2 square roots. But then we're squaring it. Is that okay? So you square the derivative, that ends up with being 2 pi from 1 to 4 square root of y, and then 1 plus 1 over 4y dy. Okay. Is that okay? So now, I mean, in order to integrate this thing, I probably should simplify it somehow. So something nice will happen if I push. See, we've been doing a lot of this today. If I push the thing outside the square root into the square root, what happens to that thing? It gets squared. So actually, I'll end up with a one big square root of y plus, you multiply that other thing by y, so y is canceled, so y plus 1/4 dy. Is that right? So I can actually integrate this without much of a problem. That 1/4, I mean, doesn't do anything. I mean, I don't even need to do any u substitutions. No, the square roots don't do that. Don't do that. No. Well, I mean, the square root of 25 is not the same as the square root of 9 plus the square root of 16, right? Don't do that. But I mean, I can just think of this as the square root, the antiderivative of square root, because there's no constants in front of y, so that just becomes So how do we do the square roots? It's y plus 1/4 to the power 3/2 times 2/3 from 1 to 4, right? Is that okay? I mean, it's just doing the square root. So 4 pi over 3, and then plug in 4. Yeah, I said 4 pi over 3, didn't I? Is that what you're laughing at? So it's 4 1/4. What is 4 1/4 if I plug in 4? What is 4 1/4? No, it's 17/4, right? 17/4 to the power 3/2 minus, plug in 1, so that's 5/4 to the power 3/2. Is that right? So this is 4 pi over 3. Now 4 to the power 3/2 is 8. And you still have 17 to the 3/2. So it's the same thing, right? 8 comes out, cancels with the 4, gives you pi over 6. And then it's 17 to the 3/2 minus 5. So it's the same thing, right? What? No, it's not bad. Okay. So I don't think one way was easier than the other in this problem. For some reason I wrote, well, maybe I was just rushing through this. Anyways, good.